Hi, everyone, and welcome to the session that Brian Putt and I, Alex Sidorenko, are doing during the Risk Awareness Week. We hope you enjoy this session. Brian, do you want to do maybe a quick introduction of your experience, and then I'll set up the context for our discussion today?
Thanks, Alex. I spent several decades at Chevron, 25 or so years doing decision analysis on major capital projects, oil and gas upstream primarily, and then retired in 2016. I've been developing training for decision analysis and doing some consulting using Monte Carlo rather than decision trees. I'm also a director of Society of Decision Professionals and a fellow certified in that organization, and work with several other organizations promoting youth decision analysis.
So, thank you. By the way, the Decision Professionals Association is one where I'm also a member of, so I highly recommend it for anyone wanting to to investigate and dive into the decision quality and decision making. So for this session today, we specifically decided to choose something very straightforward but illustrative to give you a feel, to give all our participants a feel. And by the way, use this opportunity to ask the questions underneath the video, comment, like, share this page with everyone else on your social media, because it's going to be this as simple as it gets when it comes to quantitative risk analysis, and yet it's still going to be amazingly powerful. So what we have is we have a risk of some incidents. And originally we started with an IT incident, but in reality it could be any operational risk, any incident to the equipment or environmental incident or an IT incident, a cyber incident, information security, anything you can think of. The important part to remember is we have a series of events that can happen throughout the year. And each of those events has some sort of consequence to the business. And we're going to measure that consequence in monetary terms. And then to mitigate the current risk exposure, we're going to consider a series of mitigations to reduce the risk exposure. And let's see how it unfolds. Stay with us, and I think you'll appreciate the step-by-step logic as we go through the exercise. And I hope a lot of the things in quantitative risk analysis will become crystal clear, and at least you'll realize it's not that complicated. Brian, do you want to add anything to the introduction?
No, I think I'll have some comments as we start to go through this. And you get in the details. I think what we're trying to do here is actually teach you how you might be able to do this, as opposed to, a real case study that would be very elaborate, and it looks really nice, and you see the graphics that might be informative, but you don't know how to get there. So this is really intended to show you how to do it using Monte Carlo, and I'll also say that this could be done in any type of Monte Carlo, whether it's crystal ball at risk. I'm using SIP math here, Alex and I are. It could also be done in Python or R, or whatever you want to do.
Absolutely. And the beauty of us using SIP math for this demonstration is you'll discover in a second, because it immediately updates, and it's really very visual of what the Monte Carlo looks like, because we already run the 1,000 simulations behind the scenes, and now we're just demonstrating the results. And even by changing some of the inputs, it resimulates almost instantaneous, which is a fun thing. So in our exercise, we have a few unknowns. For example, we need some data on the cost of downtime. And that's our first, orange cells are the data inputs for us. It's basically missing information, and we need to go ahead and conduct the interviews or look through the logs and look through incident reports, we need to pull that data together. It could be through subject matter experts, it could be through observation, it could be through benchmarking. We need to get that data. So the first missing point is the cost of downtime. If an incident occurs, how much does that incident cost? What are the implications? And implications could be direct, indirect, could be combination of direct and indirect consequences. So for our case study, we decided, and I'll act as the independent expert. And when Brian asked me what was the minimum and the maximum historical cost of an incident, I told Brian that the minimum, based on my data, was 20, and the maximum was 50. However, majority of the observations have been around 25. So that's a very skewed distribution.
When you say majority, though, Alex, this is the mode, I think. Is that what we're talking about here?
Yes,
This is
exactly.
the mode is the one that's most frequently is a single element. It's not the mid
Yes,
value, or it's not the expected value. It's what's most likely, right?
most frequent.
Most frequent, yes.
Yes. Yes, indeed. And in SIPMath, we, again, for illustration purposes, we decided to represent the cost of downtime as a triangular distribution. Is that
That's correct. And the reason we did that is because SIPMath has an easy way, and we'll get to this when we talk about the frequency of incidences, of adding up independent identical distributions for triangular. It becomes much more difficult with other distributions. So you could have looked at the Putt or other distributions, log normals, but some of those may be more difficult to put together to have independent costs. Let me add one other point. And I want to make sure, Alex, that you've included all the cost of downtime. It's not just the cost to repair the machine or whatever it might be, but it also might be the loss of product, or there could be some really hidden costs of, I didn't deliver the product to the customer on time, and therefore he wasn't a return customer. So you really need to think through when we talk about cost of downtime what you're including. And in fact, you may have different subject matter experts, and in a more elaborate model, you might even break down those pieces into different elements.
Yeah, absolutely. That's a very good point. And the great thing about SIPMath, in column I, you can immediately see that distribution kind of visually appear in the cell. And at the moment, it gives you the single trial, and because we set up the formula to do that, and Excel can do it quite easily, it gives you the average, which is an important piece of information. While we're saying it's between the total cost of downtime could be somewhere between 20 and 50, on average, based on the distribution that we selected, it will be 31.8 thousand or million, whatever.
But you use the word trial. What does that trial mean? Well, we said we did 1,000 trials. We could go look at multiple different trials, or not same time, but this happens to be trial 39. If I went to trial 40, now it's 22. Now it's 25. Now it's 35. So we can see all these different trials.
Yep, and in fact,
there are 1,000 of these things.
Yep, exactly. Thank you. This is a very important point, because we've simulated 1,000 trials, and while each of the individual trials are not that important to us, we can technically see them, and it's an important, I think, psychological moment where you see the cost of downtime changes in every single trial, but it's always within the parameters that we've given it. So somewhere between 20 and 50. And on average, when you take all the 1,000 trials, it will be 31.8. But we're not going to multiply the average by anything. We're going to multiply the whole distribution. And that's the beauty of Monte Carlo. So the second piece of missing information is the frequency of incidents. How many incidents have we observed in the past throughout the year? and how many incidents do we expect before mitigation, current state, how many incidents do we expect in a given year? And my inner expert tells us that we expect 7 incidents per year on
So this
average.
is the average number of incidences, Alex?
Yes, correct.
Average or the expected value, right?
Yes.
7. Okay.
And this is very important question that Brian just asked, because we are to represent the uncertainty around the incidents per year, because it could be 7, it could be 8, it could be 9, it could be 3, it could be 0. In fact, we'll talk about that in a few seconds.
I want to differentiate this from the mode. This is really not, the 7 is not necessarily the mode, it's the expected value.
Yes. We want some sort of distribution around the 7, which is our average. And so we would use a Poisson distribution that is a very nice representation of those discrete frequent events around a mean. And so we can see that in this specific trial that Brian is looking at, he had 10 incidents, in fact. And I'm actually looking at my version of the model in parallel, and I have a trial with 9. And so you can see that as trials change, the number of incidents, this looks like a lucky year, for example, with 4 incidents. This looks like a good year with 5 incidents. But on average, you will see that there will be 7 incidents per year. And so now we can calculate the total cost of risk, and that's before mitigation. Total cost of risk is, I think if you just click on that cell with the total cost of risk, it's basically a formula multiplying the cost of downtime on the frequency of incidents, but it's doing it in a very correct mathematical way. Do you want to talk about IID, Brian, and why it's important?
So the way some people might do this is they might say, well, let's take this cost of downtime and let's generate 25 identical distributions, but all independent with different seeds, okay? And crystal ball are at risk that they would all be independent to start with. And then I can just add up the number. In this case, I would add up the first 5. And if I went to a different trial, I might have to add up 7. I might have to add up 10. But what this does, and this equation here, you can say, oh my gosh, what is that thing? But SIPMath wrote that for us. We didn't have to do it. It was like 2 or 3 clicks and it was done, So that's one of the beauties of SIPMath. It's really easy. I mean, crystal ball and at risk have
they do
similar things. I don't know that they actually do the sum of triangulars or any of the others, but in any case, you can certainly get there one way or the other. But they should be independent, because if I had 5 events in the year, they're not going to have all the same identical $23,000 to mitigate.
To the consequence, and that's exactly this is a very important point. And some of the kind of basic rookie mistakes that risk managers make is then everybody knows that risk is a consequence and the probability or frequency multiplied together. But the trouble is, if you have more than a single event in a given year and you don't do IID calculation where you run independent simulation for each of the incidents that happens multiple times a year, that means your assumption is that something may happen 7 times, but every time it would happen in a given year, it would be identical to the previous time, which of course is nonsense in real life. That never really happens. And so what this could have done is that could really shrink or expand the risk, the total cost of risk unnecessarily. So it would become an unrealistic simulation. So that's why it's quite critical to model separately each of the occurrences of an incident if it happens more than a single time in the year. So let's now look at the total.
Just to
go on.
Make sure clear this perfect. I took 23 times 5 gives me 115. 115 is not equal to the 136. So in this particular case, the cost of the downtime for these 5 instances was greater than if I'd had all 5 at 23.
That is a good illustration. So we would have, if we fallen into this kind of rookie mistake, we would have underestimated our risk by just under 10%, which is which is actually quite alarming.
Yeah, in this particular case, yeah.
And sometimes you could overestimate significantly. So you really want to avoid those rookie mistakes. So the total cost of risk on average is 222,000. That's a great number, I think, for the total cost of risk.
Okay. All right. You want to go out to the mitigation now?
Yes. And so the next kind of logical step in the process is we want to say, okay, well, 222,000, let's presume that's significant and that is unacceptable to us, and we want to mitigate that because the risk exposure is too great. So we would then come up normally with a series of mitigation strategies, and we would test different mitigation strategies. But in this illustration, because we just want to illustrate the kind of the logical flow, we came up with one type of mitigation. And that type of mitigation has no effect on the cost of downtime. So the cost of downtime stays the same. And in fact, we just see it's not orange. It's not an input. It's just a basically repeat of what was above. And it's a formula. And so what does our mitigation affect is the frequency of incidents. And so based on our, again, expert analysis and our forecasting, and we'll come back to that at the very end on the accuracy of the forecasted reduction in risk. We forecast that by implementing a mitigation, the number of incidents, the frequency of incidents will change from average 7 to average 4. Okay, perfect. And the only last piece of missing information, and Brian, if you can scroll up a bit so the screen is slightly better visible. Perfect. The only trouble is that mitigation is not free. It actually costs a lot of money. And because the mitigation is not set in stone, we also have some uncertainty around the mitigation. So we estimate that the mitigation will cost somewhere between $12,000 and $20,000. And we expect the mode to be around 15. Nice. So the model has now been updated, and we will scroll down in a second and we'll discuss all the different implications. But what we can immediately see is that our total cost of risk used to be 222 on average. Now our total cost of risk on average is 142. So we actually made quite a significant 80,000, in fact, reduction in total cost of risk.
We'll take the average of this, and we can then do that, I think. So our savings is 85.
Nice.
So 95, excuse me. That didn't make sense. Oh, yeah. I know. It's 95. No. What is the savings here? It's
per year. Maybe it's
not total cost. Oh, the total cost includes.
Oh, of course.
So I don't. Well, this is the savings before. Yeah, let's just take this off here. Okay, I think that's what I was expecting to see.
Yep.
Okay,
so
there we go.
That's without mitigation. Yeah.
Hey,
and then
hey, Alex, this is another thing. When you're building a model or looking at a model, you always want to have a gut check on this. Because these things are being updated automatically, it's oftentimes easier to see your errors in the modeling. And
that's a good point.
Yeah, and if in some other simulations, you've got to take a special effort to update things. And I would encourage you, if you're using an at-risk or a crystal ball, update those things frequently. Don't wait until you got everything in before you start running the Monte Carlo.
Which is a fun exercise when you have a complex model that takes 20 hours to simulate, and every time you need a feedback on something you've done, you have to wait a long time. But luckily, computers are much faster, because I literally remember running a simulation which took 48 hours on a strategic business model once, and we would leave it over the weekend and hope that it didn't crash at risk. So we've built our model. Let's now kind of deep dive into some of the key findings and see what they tell us. So let's look at the outputs. First, Brian, do you want to tell us about this output? Because this is a very nice sanity check.
Yeah, so we talked about the frequency per year without mitigation, which is the blue line, with an average of 7. And we talked about with mitigation, which is the orange line. And this is showing the range. And this is a cumulative distribution chart for frequency. And it goes from 0 to 100%. And the way to read this is, let's say if I drew a line here at 30, it says there's a 30% chance that it could be less than, well, that's a 3.
Yep.
3, if I pick that point, it's actually, I guess 40% chance is 3 or less. It's a 20% chance it's 2 or less, right? And you come over here and do the same thing. Or you could come up here and say, for 5, there's a chance of 20%. It could be more than 5.
Yep.
Yeah.
Yep. So it's a very powerful graph. For example, when somebody asks you, well, given the mitigation, what's the probability that we will have less than 5 incidents in a year? And you can immediately say, well, 80% after the mitigation, and before mitigation, it was only 30% probability that will be less than 5 incidents per year.
Yeah. And the other thing this points out is without the mitigation, the blue line, it doesn't appear there's any chance it's going to be 0. Or a very small. I mean, it's really, really small. I'm not going to say this covers the whole space. We'd have to do millions of trials here. But over here, there is a small chance that it could be 0.
Yep. And the table on the right is also very useful. We usually show a confidence interval, like a 90% confidence interval. So, for example, you would say, without mitigation, 90% of the time, you would expect between 3 and 11 incidents per year. After mitigation, 90% of the time, you would expect between 1 and 7 incidents per year. And this is a very powerful message. The mitigation does not eliminate the risk. There is still a very significant probability that some incidents will occur, but it will be significantly less than before.
Yeah, another interesting. I mean, if you've had any statistics, you've seen the normal curve, and they show the normal curve as a nice smooth curve. And this isn't smooth. Why is that? Because this is a Poisson distribution. I can't have 5.5 incidences. I can only either have 5 or 6. Yep. So although this looks like it's just plotting, maybe 10, 15 numbers here, in reality, it's plotting 1,000 different answers. It's just that a lot of those answers were the same because it's a discrete distribution. Poisson.
Yep. Exactly. Let's scroll down and see what else we can take away from the model. So the total cost, yep, and go a little bit further down.
Okay.
Yep, it's perfect because our pictures are covering the bottom graph, so they're not distracting us.
Okay.
And this is ideal. Okay, so this is wonderful. We now have the blue line is the before mitigation total cost of risk, and the orange line is the after the mitigation total cost of risk. We can see that the averages used to be 222, now it's 142. What can you tell us about the green line?
Oh, because I talked to the decision executive, and he really wanted to have the risk below 1,000 or 100. 100. And so what I've plotted here is I've plotted the 100 to help him understand the reduction in risk at the 100 point. So the chance of being less than 100 without the mitigation is something less than 10%.
It's 6%, just because for convenience, we also copy pasted it into the table on the right. It's actually 6% without mitigation. And
okay, right there. Okay,
yep.
great.
And 27%.
27%. So that's the 27% right there. Yeah.
Yeah, exactly.
Yeah,
so that's a significant change.
I always hate to get too precise here because it's 27 or 28 or
Yeah.
Anyway, fair enough. We got, and we can calculate the numbers, and SIPBAT did this for us. They used a count if command over the 1,000 trials that we had.
Indeed. And so in the table, again, we can see the confidence interval. So normally we would talk about, with executives, we would say, after the mitigation, 90% of the time, the total losses from that risk could be somewhere between 44 and 250,000. And before mitigation, they were between 90 and 365,000. And we can also represent this risk either as a cumulative curve or as a box plot. I'm a big fan of box plots. Brian prefers cumulatives more. So we've put both of them so everyone is happy. On the box plots, for example, for me, it's almost immediately easier to see that the orange with mitigation significantly shifts the risk exposure lower. And you can even see, that there's a big chunk of it below the 100,000 threshold, which is important to the senior management, whether on the blue box plot, there's a very small, in fact, only 6% portion that is below 100.
As you're preparing your analysis, keep in mind your objective is to provide insights to the executives, not to demonstrate your graphing skills. So don't come up with new types of graphs that they're not used to seeing, because then you're going to spend all your time, your valuable time with them, explaining the graph, what are the axes and whatever. Hopefully they would be familiar with these types of graphs, and you can easily get into what are the insights that you've realized by doing this analysis that help them make a decision.
Exactly. Let's scroll down and see what else we have in store. So at the moment, and let me wrap up, because we're talking about the technical things, but it's important for us to talk about the management side. Based on the analysis done so far, we can say that the mitigation is worth it. Based on the risk analysis we conducted, it seems like the mitigation is worth it. I also see the blue line. I don't know why.
I don't know why that's there.
Yeah, why it's there. But basically, I don't know. We'll just ask people to. Oh,
there we
perfect.
go. It somehow needed a refresh or something.
Yeah. What if you press F9? Will it?
I don't know. Hit F9. Okay, I hit F9.
Yeah. It's fine. We've got the left one.
Yeah.
We did the tornado diagram, which is a very powerful diagram to answer an important question: which of the assumptions contribute the most to the total cost of risk? And because our model is very simple, it just has the frequency and the cost of downtime and the cost of mitigation. We've mapped the three things to discover that it's not the cost of downtime per se, but the frequency of incidents that has the greatest impact on the total cost of risk. So in fact, you think it may have been a coincidence, but in fact, it was very carefully investigated why we chose a mitigation that targets specifically the frequency of incidents and not the cost of downtime, because it's the frequency of incidents that has the greatest impact on risk exposure. So if we had limited budget, we wanted to have the greatest positive impact, so we focused on the frequency of incidents because that has the biggest effect on the total cost of risk. And what we discover when we did after the mitigation, the right side, which you can't clearly see, but I'll just tell you what it shows, is that the cost of mitigation actually makes almost cost of mitigation, the top one, makes absolutely no or insignificant impact on the risk, and frequency of incident stays the number one priority. So we were absolutely right at mitigating that element of the risk. Do you want to add anything?
Oh, absolutely. I want to talk about what this graph represents. This is not the typical tornado chart that you might have seen in college, where this center line here, it represents the P50 or the mode. We could have used the mode of all these things, the mid values, to come with the center line, but we didn't do that. That would be more of a deterministic tornado chart where everything's held constant except one variable that's moved to the P10 or the P90. And I might also add these endpoints here, the P10, which is a good answer for frequency, and the P90, which is a bad answer. So sometimes people think of the other way around, but you've got to think about what is the variable and how it impacts the results. So you'll notice that we had, 222, Alex, was the center line without mitigation, and this is 222 right here.
Yep.
And I forgot what this is, 142 or something of that nature over here. So that's the center line here. So this, if you've heard of value of control, this is effectively the value of control of setting the frequency equal to the P10 frequency or the P90 frequency for this case. And I'm sorry I'm not sure, I just don't understand what happened there.
That's fine.
Yeah.
Let's investigate the next graph and see what we can take away from that. So I suspect that many of the people watching us right now are struggling with this little assumption that we've done, because our expert assumption was that the current frequency average is 7, but we think that the mitigation will have an effect and reduce it to 4. So we actually went ahead and tested that specific assumption, realizing how serious that assumption is in our estimate and in the final decision. And we wanted to test, well, what if we were wrong in that reduction in frequency? What if it only reduced to 6 or 5 or 4 or 3? What if that changed? Will our decision change? And we would be happy to report to you that based on the analysis that we've done, it would be the right decision to mitigate basically with any reduction in frequency. Even if the frequency reduced on average by just 1 to 6, it's still worth implementing the mitigation. It's just the effect wouldn't be as spectacular as it was in our model, but basically any kind of reduction already provides a positive impact. And so that's a very powerful message, because when you come with the risk analysis and you say, well, we've interviewed all these experts and this is what they forecast, and then somebody absolutely always will say, yes, but what if the expert is wrong? And here we can say, well, it actually doesn't matter if the expert is or how wrong he is, because any reduction in frequency already makes this specific mitigation worthwhile.
Yeah, maybe, Alex, but if we're capital constrained, we may not have unlimited funds for these things. It has to compete against other alternatives. So what if we looked at the right-hand chart?
Yeah, good idea. Do you want to talk about the right-hand chart?
So this is the savings per dollar of mitigation costs. So what we found out was, yes, we do save money with 6, but it's only $1 per dollar spent on the mitigation. Okay, this is after taking off the mitigation cost. So it saved $2, and I spent $1 to get there, right? So I have to compare that to other alternatives that I might have, because there may be multiple mitigation alternatives, or there may be other risks within my company that need to be mitigated, and I've got sort of a certain budget for that, right? And so I need to be looking at that, or maybe there's new projects. And so what I would want to do is to find out what is my marginal benefit I'm looking for my capital or my capital efficiency, And then I could, kind of draw a line here. If I drew a line at 2, it'd say, I'm not going to do it for 6, but I would do it for 5 or 4 or 3, obviously 2 or 1. And obviously at 7, I haven't reduced the frequency, and so it's negative because I had to pay for the mitigation anyway.
Yep.
Yeah.
That's
and so that
very
makes
good
sense
point.
there.
Yeah, absolutely. That's a very good point.
Yeah, but there's another issue here. This represents the savings per year, but we only had to do the mitigation one time. So the question might be, well, what is the value of this mitigation over a number of years?
Yeah, and I think this is our kind of last bulletproof argument, because what we've just showed is we showed that within the context of a single year, that mitigation is already kind of paying for itself. It's already worthwhile doing. But that's not it. That's not the best we can do. And scroll to the bottom. We can do better, because the risk actually happens every year, and we've just taken a 10-year horizon to show that the positive effect is significantly multiplied as you look at it over a number of years. Do you want to talk about the kind of the final conclusion of our little risk model?
Well, okay, so let's make sure once again, this is that cumulative chart. And so it says, look, for our investment in the mitigation, we could save up to over $2,000, $2,000 to 200,000. That's $2 million, I guess.
$2 million. Yeah,
$2 million. And there's no chance of losing money on this. That's the savings.
Mm-hmm.
With an expected value of $858. Now, there's some assumptions that had to go in here, and that is, what is the discount rate you're going to use to do a net present value calculation? And the other thing is, hey, your costs, the cost that you're going to save would probably escalate over those years. So the costs have to go up every year, and then I'm going to discount those things back along with all the savings. And actually, this only took two or three lines in the model to calculate that. And now what we can do, the other thing that's kind of interesting, and I love doing this and explaining it, because we can talk about what are the savings over time. So let's talk about year 1 to year 10, all right? And so we've calculated the savings on per year. So year
annual
1,
basis,
yeah, but why is that a kink in there? Well, I had to spend money on that mitigation in the year 1, so that I've got a less savings the first year than I do in the 2nd through the 10th year.
Mm-hmm.
Right. And then I'm thinking that this is going to, there we go. So this is the trial. Remember we said we had 1,000 trials?
Yeah.
So here's a trial. That's trial 50. Let's see if we can get it to do something. Oh, there's another trial. So what do these bands really mean? Well, that means that in a given year, there's a 10% chance it could be higher than this line, and there's a 10% chance it could be lower than this line. And so we can actually see this. And I think it's very powerful for the decision makers to be able to see some sort of active graph, and they can have a much better feeling for what it is. I'm not always on this P90 line and not always on the P10 line.
Completely agree. I very like the message. I hope you enjoyed our little demonstration. Simple case study, but very powerful messages, and messages that you are unlikely to be able to put together without the quantitative side of risk analysis. And yet this model is lightweight, very simple to replicate, and it can be done in Excel with SIPMath. Any final thoughts, Brian?
No, I think we kind of covered it. I guess if you want to get a copy of the model or whatever, you can reach out to Alex or myself, and we'd be happy to talk you through this and get you going on your risk management. And remember, management means you need to do something. It's not just a matter of quantifying the risk. We need to actually act on it. And so unless your decision maker is going to act on your analysis, it hasn't really been fruitful.
That is a very, very important message, and the implication of that is you have to present your analysis in such a simple and transparent way that is understandable. You almost digest the kind of messages into conclusions and the words saying, well, this mitigation makes sense, 90% of the time because it reduces the risk by, this many apples. Thank you everyone for watching. Ask questions, write comments, and we'll see you in the other workshops at the Risk Awareness Week. Thank you. Bye.
Thank you.